All right, thank you so much for the introduction, and thank you, Mirko, and all the other organizers for giving me this chance and putting together this wonderful and really high-level conference. So this is the title. I want to qualify that this is exciting here is not necessarily an adjective. So with that, let me first begin by thanking the people who actually did this work. My former student, Vijay Lee, and a talented undergrad, it seems like it's not working, Zach, current student Luca, and former postdoc Shin and Sudipta. And we get our DFT support from Angel Rubio's group, some of the samples from Jim Hone, and of course the boron nitride from Japan. Okay, so by now I think all of us are kind of convinced that moiré semiconductors are a really fantastic platform to study correlated electrons. So we have seen Wigner crystals, and also together with topology, you can get fractionalized quasi-particle at zero field. So this is really exciting. This morning we heard superconductivity unconventional from GA's talk. So this field just keeps giving and giving, which is fantastic. And what I would like to highlight here is that these early measurements were done using optics. So this was exciton sensing of these fractionalized states. Even here, this is through exciton. We heard Brian's nice talk that excitons can be used as sensors. And so I would like to pose a question here that can we actually go from excitons being spectators to actually excitons creating some non-trivial quantum phases. So imagine a system of many excitons and probably even many electrons, and can this interacting system give rise to non-trivial phases like exciton-mediated superconductors or fractionalized excitons and so on. So that's a big question. In this talk, I'll just show some really baby steps that we have taken to get this field into many-body interacting excitons. And the key point here is that when many excitons interact, because the excitons are quasi-particles which can have a slightly different internal structure from their layer degree of freedom, there can be actually a transition where the internal degree of structure changes and causes some kind of a phase transition, and this is arising from an interplay of attraction and repulsion. Okay, so I'm going to talk in detail about this, but let's come back to this system of many excitons which are interacting. As compared to electrons, this is a naturally driven dissipative system, right? So the excitons are eventually going to get converted to photons, and that can be a feature here, such that the photons can serve as messengers and tell you what's going on in this interesting material that you might have created. You could also turn this around, and you can use that to generate some interesting phases of light of photons, let's say, because the matter is more interesting. So that's something, a nice key feature that we get as a bonus. But you might say, look, excitons are neutral compared to electrons, so they don't interact very strongly. And moreover, interactions are density dependent. And to create a large density of excitons in steady state is going to be challenging if your lifetime is on the order of picosecond, which it is in monolayer. And so, yeah, indeed, these are big issues. But then again, we can use these dipolar exciton that we heard in a few talks before, where the electrons and holes live in different layers. So you get a permanent electric dipole. So first of all, you can tune its energy through applied electric field. And we'll see that can be useful as well. But more importantly, these two dipolar excitons can now repel and then lead to some kind of interactions. Moreover, now, because you have separated electron and holes, they live longer. So you can have a lifetime on the order of 10 to 100 nanosecond. And the interaction time scale is on the order of femtosecond to picosecond. So for all practical purpose, this is going to happen in steady state. The interaction and the phases that we are going to create are basically in steady state. So that's nice. So just to summarize this, contrast it with the electronic system, because now we have dipolar, quasi-dipolar interactions, we can actually also get not only repulsive but attractive interactions because of the anisotropy. We can probably also tune the range to some degree of interactions. This is inherently a mixture of bosons and fermions, and that physics is also not very well explored in condensed matter. The exciton actually inherits the topology as well. So you have all the ingredients that you need to create interesting phases of matter. In addition to creating phases of matter, an equally challenging thing is to detect, especially in nanoscale. How are you going to detect that? And again, here we can actually employ the two-dimensional nature of this material, and we can do some kind of a proximity sensing by looking at, let's say, charged dipolar excitons or localized dipolar excitons or localized spins and charges to sense some quantum many-body state. So that's another direction. And while I'm on this topic, let me quickly show you in one slide that indeed you can use localized dipolar excitons to figure out charge order. So remember, these dipolar excitons can be really sharp, basically 26 micro eV is our resolution. They are very stable, and with electric field, they show a Stark shift. Right? So now if this electric field is arising from a charge order, let's say when you dope the sample with electrons, you will have charge order in this generalized Wigner crystal. And as you change the doping, these lines actually shift around, but in a very reproducible manner. And if you analyze the jumps, you can show that there is an intrinsic order in the electrons that you're adding. And this is kind of the generalized Wigner crystal. So these can sense local charge order. But I'm not going to talk more about that today. Let's bring back interactions. So I mentioned that you have repulsion between excitons, but excitons also have spin or valley, and so there can also be exchange interactions. So very naively, if you consider them as bosons, then you have two repelling bosons, and so the spatial wave function wants to be antisymmetric to minimize the repulsion. And so the total wave function is symmetric, so the spin is also antisymmetric for the lowest energy state. This kind of a triplet spin will be separated by an exchange interaction. You don't need to consider them as bosons. If you don't like it, you can do the whole, I don't want to scare you, but basically you get the same result if you consider the individual fermionic particles, electrons and holes. Right, so let's look at if this really happens. The way you can do this is if you can create an imbalance between the two valleys. This exchange interaction will kick in because it depends on the imbalance in the two valleys or two spins. And you expect then a splitting between the two valleys even without a magnetic field. So we did this experiment, and I must say, what I showed you before was for localized excitons, sharp peaks. This is going to be for so-called freer excitons, where the wave function can really overlap so that this exchange can kick in. And indeed, in such a sample, we see that if we pump with circularly polarized light, we can detect a splitting between the two valleys. The two valleys now being the two circular polarized emission. And the splitting can be, up to 4 milliV, so up to 6 Tesla of virtual magnetic field. So you don't have a real magnetic field. And so this exchange interaction is going to be useful when I come to the real message of this talk. So keep this in mind, please. OK, so that was the exchange interaction. Now, let's consider dipolar kind of interactions. If you have just these two layers, then these dipoles are always going to point in the same direction, and they are going to repel. But as we know, dipolar interactions can be attractive. So we could think of such a situation to induce attractions. And to do that, you can think of bringing another layer where if you choose appropriately, the dipoles are going to point in opposite direction. And now at sufficiently high density, these dipoles can attract, while these are going to repel, right? And you can do a simple electrostatic calculation to indeed see that, at some reasonable distances, you're going to have some attraction between these dipoles. All right, so this is going to be a key point. We have repulsion and attraction, and let's see what kind of physics that leads to. So here, we are going to consider a slightly different kind of exciton. So imagine if you have 3 layers, and the outer layers are the same, such that the charge carrier can tunnel across this barrier layer, where let's say, the opposite charge lives. So you'll have an exciton, which is essentially let's say here, the hole is delocalized over the outer layers. So it doesn't have a net dipole moment. It has a net quadrupole moment. And then there is a theoretical prediction which did electrostatic calculation and found that if you have lots of these quadrupolar excitons, then they weakly repel. But then at high density, the system might favor such an arrangement, a spontaneous antiferroelectric or a staggered configuration of dipoles, so that these can attract and lower the total system energy. So we wanted to study this. So to do that, well, this is the phase diagram. I can skip this. By the way, this is all electrostatic, completely classical, not quantum, no moiré. OK, so we considered such a structure, tungsten sulfides on the outside and selenide in the middle. And the sulfides are AA stacked, so that the hole can actually tunnel across. And now what will happen is you can think of this hybridized state as a superposition of top and bottom excitons. And so there will be 2 branches, a symmetric and an antisymmetric, when you hybridize them. The symmetric will have some weight of the electron in the middle layer, right? Whereas the antisymmetric will have a node, and that's our DFT calculation showing that. So we make such a sample with gates and so on to apply electric field, and this is what we see. So in the dipolar region of the sample, we see a linear Stark shift, as you expect for a dipole. But for the quadrupolar trilayer region, we see a nonlinear shift, which is only on the red side. So the energy is always reducing. And so we understand this in this picture, that you have these 2 linearly dispersing dipoles, which you hybridize, and now you get this symmetric and antisymmetric branches. The antisymmetric is going to be dark because of the node in the middle, slightly darker. Also, it's high energy. So we only observe in PL the symmetric branch. And that kind of actually, we can fit this and get the hybridization energy that way. That's about 10 millieV in this case. And I must also mention, Tony Hines and Souféché's group has also seen these kind of in a similar heterostructure. All right, so that's nice. We extracted the hybridization energy. But just as a check, we could use now, instead of AA stacked outer layers, we could use AB stacked outer layer. And so this is the AA stacked outer layer DFT, showing that, yeah, indeed, it's hybridized with some charge in the middle. If you make AB stacked, then it's not hybridized. And moreover, it actually breaks mirror symmetry. And so that when we make such a sample, indeed, we just see 2 branches which don't hybridize. So it's nice that, indeed, this hybridization must be taking place. How much time do I have?
4 minutes.
Oh, OK, good. I'll quickly mention what happens. So now we want to look at this, whether there can be this anti-ferroelectric ordering. So to do that, what we simply do is just increase the power, so create more excitons, more of these quadrupolar excitons. And you see what happens is, first of all, this peak actually shifts blue. That's one thing. Also, if you notice, this sort of nonlinear shape is now becoming more linear, more dipole-like with electric field. And we only see the lower energy dipole branches, so not these ones and not these ones, because they are high energy, and the system is very floppy at 0 field, so it polarizes with electric field. So looks like we recover dipolar exciton here. So some kind of a transition from quadrupolar to dipolar with density. Also notice, maybe it's not very clear, but something funny is happening at zero field. There seems to be some kind of a kink appearing there, and we'll come back to that. So to explain this dehybridization in a way, we refer to this really old paper, but fantastic paper by Schmidt-Ring, explaining how the Pauli exclusion can lead to exciton phase space filling. So essentially, this blue shift is coming from the weakening of electron-hole interaction as a function of density, and also there is a dehybridization or a density-dependent hybridization, which is happening because the hybridization is maximum at the band minimum, but if you go away, the hybridization decreases. And now with more density, you essentially are having excitonic phase space filling, and so you push out away from the band minima, and the hybridization decreases. So we assume some kind of a form for this decay in K-space, and also use the exchange energy for the weakening of the electron-hole attraction. And with that, we can actually capture very nicely our blue shift data, and also the fact that the slope changes and reaches the dipolar slope. All right, so that's good. Now let's come back to this question, whether we'll have this order. And remember, this will only happen at zero field, right? Because otherwise, you will polarize. So, this was a classical calculation. So we went slightly one step further, but not too complicated. So I don't want to scare you, but what's going on here is, instead of dealing with a many-body system, which is hopeless, we just consider two dipoles. But we consider a kind of full quantum problem, including the effect of electric field, and the many-body effects are going to come in this hybridization as a function of density. And then we have the energy of different configuration, up, 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 down, down, up, and down, down. That's our basis. And we solve this as a function of electric field and density. And so here's the main summary, which is that the blue region is a antisymmetric superposition. And because we don't have thermodynamic limits, so we cannot break spontaneous symmetry, but we will always have a superposition of up, down, and down, up. And so these states at zero field, but high density, indeed look like there will be antiferroelectric correlations. Whereas at high field, you get more polarized state, as you expect. And so this is our simulation. And we are in somewhere here about 1 to 2 to the 12 density. So indeed, this should happen in our sample as well. But how do you go about measuring that or looking for that? So let's remember our exchange interaction, right? So if the exciton is changing its internal structure, we have to somehow have a way of knowing its wave function, right? And exchange actually does that, right? So imagine if you are in this staggered configuration versus this. Here, you can exchange both electron and hole, whereas here, you can only exchange the hole. Exchanging electron is trickier because you're separated out. So what we do is we look for this exchange splitting, which I showed you earlier, as a function of really small electric field. This is really zoomed in. And you see the exchange splitting, which is shown here, actually decreases, as you expect for this state, at 0. And this is really in agreement with this kink that we see in PL, which is completely different. So we actually don't understand this kink, but somehow it tells us something funny is happening at zero field. We cannot claim long-range order, but at least we can give some evidence for this antiferroelectric correlations. All right, so I see the chairperson is getting anxious, so I'll quickly end here. So the key message I want to say is, looks like this platform is also equally interesting, maybe not equally, but interesting for studying a system of many excitons and looking at the phases that come about. And I skipped over the moiré part and the internal triangular lattice, and that we can try to study later on, because will have effects of probably frustration, given that the antiferroelectric order might be melted by fluctuations. So with that, I thank you for your attention.